All right. I've said in the last couple of talks that I did that, I'm obviously drinking water up here, but if you guys provided me with peppermint schnapps, I would be able to keep the phlegm down better, and the lecture might get a lot more interesting by the end. Voltage regulation equipment. What we're talking about here primarily is we've got substation LTCs, OLTCs, line regulators, which most of which, as we mentioned before, are automatically tap changing auto transformers, and then voltage scheduled switch capacitors. Those are the main ones. As you're aware, when I've got more than one regulator on a feeder, effectively they're coordinated, not all that differently than protection is. That we want to make sure that if a voltage regulator downstream is switching, that one upstream isn't going to change in response, and vice versa. So there's planning that goes into making sure that the amount of chattering between these things is minimized. The obvious problem that we can end up with is if I put distributed generation out on the feeder, it can change the directions of power flows locally in different parts of the circuit. Things like line drop compensation could get messed up. Some regulators may not be able to handle the negative signs on some of their incoming signals. There's a lot of reasons why this can mess up all of that coordination that went into keeping the voltage regulated on the feeder. So, and then as I mentioned before, that for synchronous generators, that's definitely true. PV has the added problem that the modulation is going like this all the time. So we have to be able to deal with all of those. This is a plot of a measured irradiance on a specific day, and I think many of you have probably seen plots like this. These are two specific ones from the high desert in Oregon, actually. And you'll notice it's from two separate pyranometers. We get a nice clear sky cosine curve type of response in the morning. Then in the afternoon, as tends to happen in that part of the world, here come those big cumulus clouds boiling up in the afternoon. And we start seeing these dropouts as the cloud shadows pass over the pyranometer. I have to toss out a couple of caveats here. You can see that the ramp rates on the irradiance are pretty extreme. But remember, this is a pyranometer. It's 1 square centimeter. So it's a relatively small device. If I spread this over a PV array of relatively large extent, that is going to moderate the ramp rates somewhat. But you can see the depths of some of these cloud passages. The shadows are dark. And when that passes over the array, the irradiance can drop from close to about a kilowatt per square meter, which you can think of as 1 per unit, down to as low as about 0.2 per unit. And we've seen cases in the field where relatively large PV plants can do that 100% to 20% drop in 4 to 8 seconds. So it's a significant ramp rate. Oh, there's one other thing I wanted to mention on this slide. I find this curious, but you'll notice right before the ramps start in the afternoon, you see that the irradiance actually goes up. Does anybody want to venture a guess as to why that happened? Go ahead.
The reflection off the clouds.
Bingo. That's exactly it. Yep. You guys nailed it. Yeah, I mean, those clouds are white. So basically there's a natural concentrator throwing some of the sunlight back to us. And you see about what time of day it is. The sun's still passing over solar noon, but the clouds are still west of us rolling east. That's exactly it. Perfect. So we get these cloud reflection effects. There's also what's known as a cloud edge effect or edge enhancement, where as the sun is passing behind the cloud, these are droplets of water. Well, they act as lenses. They will lens some of the sunlight around the cloud down to the array. So before the drop, you'll see a little spike that shows up. These things sound kind of odd, but they actually are significant and measurable. And there are inverters with fast enough controls that they can see those. They may not follow them exactly because of the speed of them, but they will track them to a certain extent. So those kinds of variability do show up. So this is the sort of variability that we're going to have to deal with from these inputs to our system. Again, with the caveat that the ramp rates aren't as fast as shown there. Here is the output power from a PV plant and the voltage at the PV plant's point of interconnection during the passage of a cloud shadow. The top plot there shows the output PV power. This is a 1.4 megawatt PV plant. So you can see it's cruising along right about 1.4 megawatts before the cloud comes. Then we get the shadow passing over the array. It ramps down to approximately 20% of its rated output power. Cloud moves away and it ramps back up. The corresponding voltage is in the bottom plot, and you can see we started at about I can't remember exactly what it is, about 1.06. It's just a little bit hot, but not much. So it's running a little bit above 1 per unit, and then it drops to approximately 0.94 per unit. So we've got a little bit bigger than a 6% drop. Now, that's a sizable voltage drop. And as you can see, I locked the voltage regulator in this case. So the tap changer is fixed. It's not trying to change. What would happen if we let the tap changer go ahead and switch? What would have happened? The tap changer would have done this. I'm sorry?
Size some solar installation. They size some solar installations by like 1.5 above, with the inverter. Can it actually output to the system? Does that mitigate this problem to a certain effect?
That is an excellent question. The question is, back in the day, you're talking about the DC to AC power ratio in the PV plant. And what we used to do is that the DC power rating of the inverter, of the PV array, was on the order of about the same as the AC power output rating of the inverter. So you would end up with roughly 1-to-1, maybe about 1.1-to-1 ratio. Now we're seeing much higher DC to AC ratios, 1.5, 1.6. And the question was, well, as I raise that DC to AC ratio, does that mitigate this? And the answer is yes, it does. Because the inverters are already full throttle, they're maxed out. They're not max power tracking. So sometimes some of those divots actually will be completely in that space of capacity that's above where the inverter is operating now. So yes, a lot of the smaller transients will in fact go away, and the bigger transients won't be as big. That's one benefit to doing that. I don't think that is the reason that it's done at this point. I think for the most part, as module prices have fallen as much as we showed there before, inverter prices have come down, but the inverter has become one of the costlier parts of the system. So it's about maximally utilizing that inverter resource. That's why they're upsizing the DC side so much. But it does have the added benefit of reducing a lot of these kinds of variability. So thanks for the question. The answer is yes, it does. If you don't have that going on, though, the regulator is going to try to catch up with it, and then you're going to see something that looks like this. This is a fairly fast regulator. You can see that the change interval is real short on this one, but it's a standard 0.5% per tap regulator. And as we mentioned before, there were several 0.5% in the voltage difference. So the regulator starts banging away to come down, try to catch this, and then it starts banging back up. That's going to wear the regulator out fairly quickly. And we've seen some anecdotal stories of where the number of tap changes per unit time for a regulator jumps up by a factor of 5, maybe even a factor of 10 in some cases, after a PV array goes in. And usually the reason we learn about it is because 6 months after the PV plant went in, the regulator fails. So obviously this is an issue that we want to try to take care of. Now, I should actually put this on the slide, and it's a good point that one thing you can do is you can really upsize your DC to AC ratio, because then the level of modulation decreases in the first place. Sometimes that's not possible if it's a rooftop array, you're space constrained. There's obviously costs associated with doing that. But what you can do, and what we do most of the time today, is we operate the plant off of unity power factor. So we're going to have it absorbing some VARs, sinking VARs. So the PV plant is sourcing watts and it's sinking VARs at fixed power factor. Now remember, if I fix the power factor, that's the same as fixing the ratio of Q to P, the reactive power to the real power of the PV array. So what that means is that for the fixed power factor, as the real power drops as the cloud goes by, the reactive power also comes closer to zero. It's negative and coming up. But what you get then is the real power is trying to move the voltage this way, the reactive power is doing this, and they cancel each other out. And if you choose the right power factor for the circuit impedance at your point of interconnection, you can completely eliminate the modulation coming from cloud shadows if you do this. So that's the most popular way for handling this today, if an issue appears. Longer term, there are a lot of cases where you'd really like to be able to do this with energy storage. We've done a plant like this. What we did is that the battery inverter system is tied to the same point of common coupling as the PV plant, and the battery system, BIS is battery inverter system. There's another acronym that I forgot to define. We use BIS instead of the IEEE standard BESS, which stands for Battery Energy Storage System, because with BESS, it's not clear whether the inverter is included, whereas with BIS, it's totally clear. So if you have a BIS, then you can have it monitor the power output of the PV plant. And the BIS is controlled so that the power to the grid is equal to the windowed average of the power from the PV plant. So basically just using the BIS as an active power filter. And it smooths the PV output power based on some averaging window. There are some rare cases where the X over R ratio of the feeder is actually less than 1. It's more resistive than reactive. It doesn't happen often, but it does happen. And when it does, usually it's on a rural feeder. So it'll be our part of the world where things like this happen. We've seen it in California too. The specific case in California that I'm talking about here was a case like this, where the X over R ratio was less than unity. In a case like that, you really can't mitigate the problem with VARs because you would need more VARs than watts to offset the problem. And you'd have to have a massively derated inverter to do that. So you might want to, under some of these circumstances, think about doing it with the BIS. Right now, that's not economic, of course. We did it largely as a demonstration project on this specific case that I'm talking about, but it can be done. The technology is definitely there. We're just waiting for the costs to get to the point where it's more attractive. So let's take a closer look at this fixed power factor. And I mentioned also that you can do scheduled power factor. Even before the advent of grid support functions or smart inverter functions, a lot of inverters had the ability to do a time-scheduled power factor. Not all that dissimilar from time schedules on capacitors. So, but what you can do is you can fix the power factor for absorbing VARs. And the case that you see here is the top plot is the real power from the PV plant. The bottom plot is the reactive power, and this is power output. So see the red trace is non-unity power factor. The blue trace is unity. You'll notice for the real power, the top plot, the blue and red traces are on top of each other because it doesn't matter what the power factor is for the real power. In the bottom plot, the reactive power then reacts as the cloud passage moves over. You'll see the reactive power is negative because we're sinking VARs back into the PV plant. When we do this, and I believe, yes, there it is on the plot. This is a power factor of 0.98. So it's still a relatively high power factor. We didn't have to change it much. And when we did that, the result looked like this. That you can see with the red trace, again, that's the one that's off of unity power factor, we're able to almost completely mitigate the voltage impact of the cloud moving over. You'll notice the voltage actually does rise just a little after the cloud moves off, and that was because of a controller problem in the inverter. That is a solvable problem. So if you look at the first part of that transient, that's the important part, and you can see the inverter was having trouble tracking the upward ramp, is what was going on there. But the point that I want to make is that you'll notice we can pretty much completely flatten out the voltage profile during the cloud passage by choosing the right power factor for the circuit impedance that we have at that point and for the size of PV plant that we have. So this is a very effective way of eliminating a voltage modulation problem should one occur. There's obviously some ramification to this because then the utility has to supply those VARs. So it's not like it comes for free, but it can be done and it does solve the problem. Now, in the farther term, I've mentioned this several times in the presentation. This is that volt-var droop characteristic that I've been mentioning. This type of a function is a function that's going to be built into inverters, I think pretty much most inverters going forward, because of the drivers of things like the new California Rule 21. What we're going to have in inverters is a curve that looks like this, where you see that there are 4 voltage set points on there, V1, V2, V3, V4. Those are all user settable. And if you look at it, you can tell it really is just a volt-var droop characteristic. V2 and V3 enable us to build in a hysteresis band. So there can be a band right around the nominal voltage where the inverter is not doing anything with VARs. In practice, when we have put these in, we have usually pretty much eliminated that hysteresis band. We've got V2 and V3 just right on either side of unity. But then you select V1 and V4 to control the slopes. How aggressive do you want these volt-var controls to be? The values that are shown on there are values that at the time we made this plot were considered to be typical or maybe default values. We've been recommending a little tighter settings than that because by the time you get to 0.9, the inverter is getting pretty close to its undervoltage trip limit anyway. But we've been recommending that people bring these in just a little bit. But when you do that, bear in mind that now this is closed loop control. And the slopes of those lines effectively are your gains in the feedback path. So you have to be careful if you've got more than one photovoltaic plant on there, that they are properly coordinated so that these volt-VAR controllers don't fight with each other. And again, modeling is an easy way to do that. So this is where we're probably headed in the future, adaptive volt-VAR control, so that the inverter will figure out whatever its VAR output needs to be to try to meet specific voltage goals. We mentioned the capability curve before. If I require the inverter to sync VARs, does that restrict the real power output? And there was a time when the answer would have been yes. Most of us, of course, have seen the power triangle. So I've got my real power P, my reactive power Q, and the apparent power S then is the hypotenuse of the triangle formed by P and Q. We're going to get an ellipse. Usually it's not quite a circle. We don't have quite the same reactive capability as real power capability. I've exaggerated the eccentricity of the ellipse just a little bit so you can see it. But it's not going to be quite circular. But you can see that with a lot of inverters that we had in the past, if they sold you a 1 megawatt inverter, that was a 1 MVA inverter. So if it was actually producing 1 megawatt, then that red P vector was all the way out to the edge of the ellipse, and there is no reactive power capability. So back then, the answer would have been yes. If you required non-unity power factor operation, there would have been some penalty. It's not as big as you'd think, because how often is the inverter really operating at max power? Especially with the DC to AC ratios where they used to be. It didn't happen all that often. So usually there was still some VAR overhead. But what has begun to happen is, as utilities have required these VAR capabilities in inverters, inverter manufacturers have responded by doing exactly the same thing that synchronous generator manufacturers do. They rate them at non-unity power factor. If you buy a sync gen, you're going to get 1 megawatt, 1.2 MVA, or something like that, right? It'll be rated at 0.8 power factor sourcing VARs. So what the inverter manufacturers are doing is say, yeah, this inverter is 1 megawatt, 1.1 MVA, 0.9 power factor, and then it can go either absorbing or sourcing VARs. So same thing, they're derating the inverter so that that VAR capability is always built in there. So the capability curve issue really has sort of ceased to become a problem for the most part. There's some other things you have to watch for with regulators. We talked about chatter, right? You can have voltage regulators that chatter with each other even if there is no DER on the circuit. But with DERs, it can become a little more challenging because the regulator generally is looking downstream from itself, saying, I'm trying to control the voltage that way. And if you've got line drop compensation, then it may be envisioning a point downstream from where it is connected. If I put DERs in there, it can change the definition of upstream and downstream. So the regulator may struggle with this. Some regulators have trouble with reverse power flow. The controllers may not be able to handle negative inputs and things like this. Almost all the manufacturers of regulator controllers now have devices that can handle this. So really the mitigation solution is just to replace them. It's not that big of a deal. That's pretty easy to handle. One situation that we have seen a couple of times that you have to watch out for is you may have a situation where there's a branch point on the circuit. So you've got a circuit that branches out. There's a regulator just upstream from that branch point, and there's a PV plant down on the end of one branch. If this PV plant is big enough that it might export past the regulator is responding to that export and the power flow in this direction, but it can't even see this branch. So it may lose regulation on one of the two branches, the one that doesn't have the DG on it. There are a number of things you can do to mitigate that. One thing, of course, you can do is just move this regulator here, put another regulator here, just regulate the branches independently. Oftentimes, that's the easiest one. One thing you can do is you can actually put communications from the PV plant to the other branch, and then you can give it some situational awareness of what needs to be done to make sure both voltages stay regulated. And then the PV can actually help you solve that situation. And what you'll want to do, of course, is the one that's less expensive. Generally speaking, I think that's probably going to be adding a second regulator, but it depends on your circumstances. So the main mitigation strategy for a case where a voltage regulator is being impacted by the voltage modulation of a PV plant is to operate off of unity power factor absorbing VARs. Ultimately, we want to look at volt-VAR controls as the long-term solution that's going to provide more benefit to enable the PV to help flatten the voltage profile of the feeder. Okay, so the next module is actually fairly long, so let me stop and ask if there are any questions before we do that. Next topics we're going to talk about are fairly hot issues for us right now. Various forms of temporary and transient overvoltage that can be caused by distributed energy resources. The question always arises when we're talking about temporary and transient overvoltage: how much overvoltage is allowable? The problem is we really don't have the type of acceptance criterion that we would like for this kind of situation. We're all aware of the ANSI C84 standard that gives us the A and B operating ranges for voltage, but that's a steady state standard, so it's not really applicable to this situation. The criterion that we tend to use is the CBEMA curve, the ITI curve, which is the one that's on the screen in front of you. Many of you are probably already familiar with this. And I'll tell you right up front, that's a little bit of an abuse of this curve because it's really not designed for this. But what we would really like to see at some point is some kind of a set of curves that is based on damage curves for different types of equipment, and then looking at what the most conservative points are at each point on the damage curve, so that you will get a criterion that can be applied at the feeder voltage level. What this CBEMA curve is it's basically that, exactly. It's just not designed for distribution application. But we use it anyway for lack of a better option. You can see what this thing does is it defines those two black lines that are the envelope that you need to stay within. So you can have an overvoltage, but it just has to be kept short to stay within those black lines. You see the red text that says need to keep the voltage out of here. That's where we're above that top black line, and that's where we'll start blowing stuff up. So we definitely want to stay out of there. If you're below the bottom black line, you'll see that's labeled the no damage region. Things may malfunction, they may drop out. So you still want to stay out of that region, but usually we're not talking about destructive failure there, so it's less of a serious issue. So what we want to do is stay between those heavy black lines all the time. I want to give you one quick definition. We talk about temporary overvoltage and we talk about transient overvoltage. And I have a good friend at EPRI, his name is Tom Key, that keeps me honest on terminology. So I have to credit him with helping me to make sure I keep the right historical perspective on keeping some of these terms straight. When we say transient overvoltage, we're talking about, I think, what people would think of. You notice the blue curve, transient, that damps out. The top of that transient curve is what we're going to call our transient overvoltage. So it's the peak that we see during the transient. A temporary overvoltage is an overvoltage that occurs during a temporary condition. So it can be much longer lasting. It might not be a real short temporary overvoltage, but what is temporary about it is that it's an abnormal operating condition. I drew it here as it's the voltage that the transient stabilizes to. So whatever the abnormal condition is that caused the transient stabilizes out, then what's left over for several seconds or maybe even many minutes is your temporary overvoltage. So just a matter of definition. And of course, unfortunately, both of them could be abbreviated TOV. So we use the lowercase r, TROV. We were laughing yesterday that, since we use current, since we use I for current as electrical engineers, we could have called this anything we wanted to. So we will stick with like gamma OV or something like that. Pretty soon we can make language a complete barrier to understanding. There are two key overvoltage mechanisms that we're going to talk about today because they're the ones most important for us as we're looking at some of these DER deployments. And that's ground fault overvoltage and load rejection overvoltage. We'll define them both in a minute. I wanted to point out that there are other mechanisms that do exist. We've got ground potential rise if you've got like ground return current or something like that. This is your step potential. There's some other mechanisms that are important from a circuit perspective, but they're not necessarily directly related to a DER installation. So we're not going to talk about those bottom three. The top two are the ones that we're really focused on today. Before we get into them in detail, I wanted to rank overvoltages a little bit to try to give us some perspective about how these different kinds of overvoltages stack up in terms of their severity. So the plot on your left shows the typical magnitudes of different overvoltage mechanisms. The plot on your right shows their typical durations. On the left, you can see the big tall one that sticks up to 25 per unit overvoltage. That's a direct lightning strike. In other words, a lightning hit directly to a phase conductor. Lightning packs a wallop, as we all know. The next one that goes up to about 10 per unit, that would be an indirect lightning strike, say a lightning strike to a supporting structure or something like that. Both of those are big overvoltages and much larger than the overvoltage mechanisms that we are going to talk about today in terms of magnitude, but they're also much shorter. So when we design for those, typically arresters are designed to handle these big pops, but for relatively short periods of time. The middle one there that goes up to 5 per unit, that is a ferroresonant condition. And ferroresonance is one of those things that can be kind of scary, because we were examining a case here not too long ago where a fairly large photovoltaic plant had all of its inverters destroyed because of an overvoltage. And we spent some time looking at it to figure out what happened. And it was a big plant and had several miles worth of underground collector system at 34.5 kV because of just the spatial extent of this thing. That was all underground. So 34.5 kV and underground, there was a lot of capacitance in that collector system. And what happened was they had a GSU transformer that went up to, I'm going to forget the voltage, I want to say it was 230 maybe, but it was a transmission voltage. And what happened was the high side breaker on that transformer popped. So the PV plant was isolated with only the capacitance of the underground collector system and the shunt inductor, the nonlinear magnetizing inductor of that GSU transformer. And that, big capacitor, nonlinear inductor, that's where you're going to get ferroresonance happening. That situation was bad enough that it caused huge problems in the plant. The mitigation in that case, by the way, was just pop both breakers. Don't just trip the high side one by itself. But you can see that ferroresonance, under the wrong circumstances, can be a very scary situation. It's kind of hard to know when it's going to be a problem. So there are lots of papers written on this, and we can get into that later, but that's not really the subject we want to talk about today. The two we wanted to get into today are load rejection and ground fault. You notice that I put about 2.5 as a maximum magnitude for load rejection over voltage. We'll come back to that in a minute because I actually think that number is probably too high, but we'll describe why in a minute. Ground fault over voltage, you'll see the theoretical maximum magnitude sits at 1.73, and some of you may have already identified that as the square root of 3. There's a reason for that, and we'll come to it in a minute. But you'll notice the durations are considerably longer. Load rejection over voltage depends on what's going on, but it could last for several cycles anyway. A ground fault over voltage, depending on the system configuration, could persist for quite some time. And that's why we worry about it, that it's not the magnitude of overvoltage, but it could cause things to just sit there and burn for a while, which we don't want. So let's take those two mechanisms individually. What is a ground fault overvoltage? GFOV can happen if I have an ungrounded voltage source that is feeding a 4-wire circuit. So by 4-wire circuit, I mean we're assuming there's a multi-grounded neutral. And then the ungrounded source continues to feed that circuit after the circuit has been disconnected from the substation transformer. Normally, that substation transformer is going to be grounded Y on the low side and delta on the high side. In some cases, it may be like a buried tertiary winding transformer. But the point is that there is a zero sequence path to ground for the circuit that is provided by the substation transformer. When we pop the substation breaker, the feeder breaker, we've lost the connection to that ground connection, the zero sequence connection. And if the generator doesn't have one, then the whole feeder doesn't have one. When that happens, you're corner referencing the system. So basically, if you look at the voltage vectors, which we will in just a second, the whole thing shifts in such a way that the unfaulted phases can go to the line-to-line voltage above ground instead of the line-to-neutral voltage. And that's where the square root of 3 factor comes from. So if we look at the voltage, I guess I'm going to show you the circuit first. We've got our 4-wire circuit, ungrounded 3-wire sources. Now, of course, we'll come back to the ungrounded sources in just a minute. But you notice I've got all these interrupters all over the circuit. I'm going to pop this one over here, this SR1. Notice that just turned green. So if we do that, we've now lost the connection to that utility ground source. If these generators continue to feed the circuit, we have to beware that we don't end up with a ground fault over voltage situation, which would arise if the voltage vectors did something like this. You notice the case on the left is the normal one. The neutral should be at approximately 0 volts because everything is balanced, everybody's happy, the phase voltage vectors are all equal in magnitude. Now move to the plot on the right. I'm going to take phase C and fault it to ground. And for right now, let's just assume a bolted fault, 0 impedance. So the voltage on phase C becomes the ground voltage. The neutral was already multi-grounded, so the neutral and phase C end up at the same voltage. But remember, and I've now disconnected this circuit from the substation. So it's being fed by this ungrounded voltage source. The voltage source, because it is ungrounded, doesn't know where 0 is, right? All the voltages are relative to each other. So let's say this is a synchronous generator. It doesn't have a ground. Remember, the synchronous generator is totally driven by Lenz's law and Faraday's law. We've got these conductors moving in magnetic fields. The sync gen says, no, I want phases A and C to be 480 volts apart. I don't care what you say, right? Because that's what my physics determine. So it's going to hold phase A 480 volts away from phase C. But now the neutral and phase C are on top of each other. Anything that was connected A to neutral is now effectively connected A to C. And that's where we get our square root of 3 overvoltage. I should point out the square root of 3 value is theoretical. In practice, it never goes quite that high because we don't have a perfectly 0 impedance fault and other impedances in the system and some other things like that we'll get to in a minute. But we'll stick with that as a theoretical max for the time being. If I look at the symmetrical components, you may recall that if I do a vector summation on these things, I add the vectors tip to tail. If the vectors don't form a closed triangle, then I have a 0 sequence component. And typically that's what happens when I have a ground fault overvoltage like this. Again, remember the generator is trying to keep the 120-degree phase angle separation between the phases so they don't collapse in terms of the angles between them. But the phase C to neutral voltage has gone effectively to 0. I drew a little bit of one in there because, again, it's not going to be exactly 0. But the problem is that VCN collapses. I can't close the triangle and I get this big 0 sequence component. And that's where the ground fault overvoltage comes from. Here are some sequence networks of a distribution circuit. This is before the fault, and I've drawn in a photovoltaic plant in here. Now what you're going to start to see is we're going to start picking up that notion again. Remember the synchronous generator is a voltage behind impedance. The PV plant here is a current source, a power-controlled current source. So that's what shows up there in the positive sequence network. You see VA1, that's my voltage source, which I'm assuming right now is purely positive sequence. Then there is a source impedance, positive, negative, and 0. And notice there's that Z0 ground sub. That is the substation provided path to ground. So that's going to be the 0 sequence impedance of the substation transformer, whatever grounding impedance we have in there, and then the impedance to remote earth of the substation ground grid. So that's what shows up there. I've got a source impedance, positive, negative, 0, that's Z1 source, and so forth. There's a line impedance, positive, negative, 0. That's the distribution transformer. It's our GSU transformer, positive, negative, 0. You'll notice the way that's configured right now, it's assuming the GSU transformer is YG-YG. So there's no delta winding, and both Y's are grounded. Then we've got an impedance in there for the inverter. We'll come back to that in a minute. You have to take that one with a grain of salt. But then the inverter shows up in there. We've got a Norton equivalent, but usually that shunt impedance, Z1 inverter shunt, isn't important for us. There's the positive sequence inverter current. And then you'll notice in the negative and 0 sequences, the inverter presents us with a high impedance. It's basically an open circuit. In the 0 sequence, most inverters actually are an open circuit. Negative sequence, it's just a very high impedance maintained by the fact that the inverter controls are trying to keep that as a positive sequence current source. For most inverters, now I should point out, there are some inverters on the market today that don't do that. And we'll have to talk about that a little bit separately. Most of them do, so we're going to stick with this. Now we add a fault. So you notice from the previous diagram, we've now added in the coupling between the networks that happens when a single phase to ground fault occurs. I have placed the fault on the low voltage side of the GSU transformer. We could put it anywhere. For the sake of argument, it doesn't really matter where we put it. So we've completed the circuit through 3 times the fault impedance. I've shown the fault impedance here as purely resistive. And I'm sorry, there's one thing I meant to point out on the previous slide, but it's still here, so I can point it out here. You'll notice I dashed in some loads that are connected in the line impedance section there. The reason why that's in there is going to become apparent in just a minute, but it has to do with the fact that now, again, the inverter is acting as a current source, right? Not as a voltage source. So we've drawn in the fault, and now the next thing we're going to do is open the utility breaker. So between that slide and this one, you notice a gap has shown up between the source impedances and the line impedances. So now the feeder's isolated. It's being operated by this 3-wire source. So the thing that worries us about this is we notice we do not have continuity in the negative or zero sequence paths from the generator itself, from the PV plant itself. Where does that continuity come from? Well, this is why it becomes critical that if you're going to talk about the sequence networks, when there's a current source in there, I have to put in the loads. That's the continuity. That's where the path is. That always scares us a little bit as power engineers, but that's where the PV current was going in the first place, right? This isn't an overcurrent. It is the current. It's the PV output current. When we do symmetrical component formulations in general, we tend to leave out the loads. The reason for that is because usually what we're using this for is we're trying to calculate fault current. The usual source that we're talking about is the utility source. It's the voltage behind impedance. So the fault current is much, much larger than the load current. And by dropping the load impedances, effectively we're dropping out the load's contribution to that fault current, which is okay. The problem now is I got a current source. That assumption is no longer true. So we need the load in there in order to properly model how this system works when it is being fed by a current source during the single phase to ground fault. So that's what we're talking about here on this slide, that although it does seem a little bit scary, we need the loads in there to properly model the circuit continuity. There's one other thing too that I didn't mention on the previous slide, but you'll notice that the loads do not couple the positive, negative, and zero sequence networks. And for those of you familiar with such things, you will realize that what that means is I've assumed the load is balanced. Well, that doesn't happen on distribution feeders, right? We're always at least somewhat imbalanced. So technically, I should have some pre-existing coupling before I put the fault in there. There should be some pre-existing coupling between the sequence networks. Understand that I'm not trying to bash the symmetrical component method for evaluating. The symmetrical components still work. They're still right. It's just that to really get this model right, with our standard formulations, we can do back of the envelope, standard circuit analysis and come up with some pretty good predictions using sequence networks with utility source. That becomes much, much harder to do when I have an inverter out there because the networks are much more complicated. And as we mentioned before, I've got this software definition aspect of the inverter. So if we need to handle this more accurately, generally speaking, you're going to want to go to some form of a transient model. So how would I model this? We're going to look at it. Here is a really simplified schematic diagram of a ground fault overvoltage situation with a synchronous machine. It's a 3-wire diagram, I guess. You notice I've got my synchronous generator over on the left, and it's shown as 3 voltage sources. Now, technically, I really should have shown those as delta, but we can make the transformation. You can see the basic principle from here anyway. Then there's that neutral point, that N, the capital N, that's the center point of the generator voltage vectors. But this, for the time being, we're assuming, is an ungrounded synchronous generator. Of course, we would never actually install an ungrounded synchronous generator, but for the sake of argument, assume that we did. So that N really isn't tied to ground. The generator doesn't know where N really should be. It's just relative to the other 3 voltages. If I fault phase C to ground, you see VCN, got the little lightning bolt down there to the neutral. Now what happens is I've got a voltage VNN. The voltage between that middle point and true ground is ECN. It's the back EMF that's produced on that phase. So that's what's happening here, that the N point is not ground referenced, and it gets pushed out into the middle of the triangle by the fact that these voltages, the phase-to-phase voltage relationships, are being enforced by the generator. That thing that I said before about how the generator says, look, I want A and C to be X volts apart, no matter what. So the generator is forcing those phase-to-phase voltage relationships. Now we look at an inverter. I guess I already said almost all of this, but because the synchronous machine is well modeled as a voltage behind impedance, that's why we end up with this issue. One thing I should mention on this slide is that the generator, of course, does have controls. It's got a governor and that sort of thing. Do you need to model those? I'll show you an example here in just a second where it depends on what you're looking for. In fact, I'll show you that example right now. Here are the positive, negative, and zero sequence voltages from an ungrounded synchronous machine undergoing a single phase to ground fault. So this is a GFOV situation. You'll notice that the time axis on this chart starts at 15 seconds. What was happening before 15 seconds was letting everything settle at steady state. So that's what's over to the left. Then at 15 seconds, we fault phase C to ground. You'll notice there's a brief spike there where the voltages pop up and they're kind of flat for a little short period. That's for about 100 milliseconds, and that's the period where the fault has hit, but the utility breaker has not yet opened. So we are still feeding the fault. In 100 milliseconds, that breaker pops off. And now you'll notice the generator is feeding the fault. What happens almost immediately is that zero sequence component jumps way up. It's basically equal to the positive sequence in this specific case because it's a bolted fault and a number of other situations. But this is our ground fault overvoltage situation. Now you'll notice, does it get to that ground fault overvoltage and stay there? No, it doesn't. It starts to fall off. Why? Well, this is the reaction of the governor trying to pull the thing back in because now there's a big load on the generator and the frequency's crashing. A lot of that's not seen in this plot. Hopefully you can also see the very dim red text that's across the bottom of your screen. There are under over voltage and under over frequency relays on this generator that have all been turned off for this specific case. And the reason we did that is so that you can actually see the transient, right? In reality, this generator would have popped off, I'm trying to remember exactly where, maybe about 15.6 or something like that. But it would have gone out on under frequency way, way earlier than what is shown on this plot. But so that you could see the entire transient behavior, we just turned those relays off. Bear in mind that this generator would have tripped a lot faster. The situation isn't as bad as it looks. But what we're really concerned with here is that peak, the peak load rejection overvoltage that happens right there at the beginning. And that is not, you really don't need the full transient model for that. So that's what happens with a synchronous generator. And remember, the key to all of this is the synchronous generator is enforcing phase-to-phase voltage relationships. That's why it looks like this. Now we're going to look at a case that has an inverter in there. And you see the same three-line diagram. The inverter, again, is not grounded. And I should point out that, I think I might have mentioned this before, generally speaking, inverters aren't grounded. They do appear as three-wire sources. So the concern was definitely a valid one, at least at first. We started investigating this. But the inverter, now we've replaced the voltage sources with current sources, which is what the inverter is trying to do. Notice they're all approximately equal. So we're trying to maintain a balanced positive sequence output current. Now I'm going to fault phase C to ground, and the voltage then, that VNN, is just going to be whatever the current IC is flowing through that impedance Z. Well, in this case, the Z is the impedance between the inverters and the point of common coupling, and that's deliberately designed in the plant design phase to keep that voltage below maybe 2% voltage drop, something like that. So it's going to be very, very small. And the bottom line is you can see that the ground fault overvoltage mechanism that exists in synchronous generators does not exist in inverters. And this is an important point to bring out. Because the inverter is modeled as a current source, it is not enforcing phase-to-phase voltage relationships. The inverter sees the voltage drop in phase C and it says, okay, keep sourcing current into phase C. So the inverter is also very fast. We talked about this before, that the controls are going to kick in and start working right away. So you really do need the controls aspects to be properly modeled. But the point is that this mechanism of moving the neutral point out into the middle of the triangle does not happen with an inverter. So the traditional ground fault overvoltage mechanism does not exist with inverters acting as controlled current sources to the grid. Well, of course, there's some caveats. This is where we start throwing in all the quid pro quos and liability limiting clauses. Does that mean that, there's no problem? There's no ground fault overvoltage issue ever? Well, not entirely. If you have, for example, what if you have a GSU transformer that is delta on the feeder side, grounded Y on the inverter side? We're seeing less of these. We were just talking about this a minute ago. That most inverters don't want to see a grounded Y on their side anymore. But let's assume that I've got a transformer that breaks the zero sequence path to ground. So it's not a YG transformer. Maybe delta on the high side. It may be floating Y on the low side, something like that. Well, what happens in that case is the inverter now has no ground reference on its side. It doesn't know where the neutral is. It's sourcing that power into the transformer. And the transformer, like if it's got a delta on the feeder side, for example, the delta windings of the transformer will enforce phase-to-phase voltage relationships. So now we actually can get a ground fault over voltage on the feeder side where the delta is, or where the zero sequence path has been broken. So is it true that you never have a GFOV with an inverter? No, not quite, because it depends on the transformer too. So you can get a GFOV if you're on that side of the transformer. And by the way, that doesn't matter what the distributed generator is. You can have whatever you want on the downstream side of that transformer. That because the deltas will enforce the phase-to-phase voltage relationships, you can still get this issue. So if there's any source over there at all. I mentioned here if you have a purely ungrounded, just a straight 3-wire circuit, no neutral, then you've got all line-to-line connected loads. Well, you'll definitely get a ground fault over voltage there because the entire delta will shift, right? You're corner referencing the delta. But it remains an open question as to how big of a concern that is because the loads are all line-to-line. They're already exposed to the line-to-line voltage. You have to watch out for arresters because a lot of times in a system like that, the arresters are still line to ground. So there may need to be some reconfiguration or consideration there. One important point is that you can have a ground fault over voltage and a load rejection over voltage, the next one we're going to talk about, at the same time. What does that mean? Well, I mentioned just a minute ago, one of the things that happens with the ground fault over voltage is, let's take phase C again. Fault phase C to ground, phase C voltage vector collapses. The inverter says, hey, I'm happy, I'll just keep sourcing current into phase C. But remember, this is a power-controlled current source. Well, I just lost a third of my output power. So the inverter's controls are going to say, what's happening is I've still got power moving in from the DC side that now cannot go out on the AC side. So the DC link voltage, that capacitor on the DC side, that voltage starts to shoot up. The inverter regulating controls are going to say, ooh, problem, open the throttle. Try to get that power out, try to keep the constant power aspect going. So what will happen is that it will extend all three of those current vectors. It's still trying to maintain constant positive sequence balanced output current. But what's happening is that part of the power that went out on phase C now has to go out on A and B. Right? So I've got whatever load was on A and B, and now I'm pushing out more power. Well, that's a load rejection over voltage. So we get a load rejection mechanism. It's power rejection to the unfaulted phases that is happening because of the ground fault. You can see how this starts to get really tangled up in a hurry. So we're going to talk about that in a minute. The reason why it's important to separate those is because when that happens, it's not necessarily zero sequence. You can have a big negative sequence component. So the mitigation changes. That's the reason we have to keep it separate. I've got one bullet here on the bottom that we're not going to talk about a lot today, but there's still some question about if I have a three-phase system that is made up of single-phase inverters. In some ways, single-phase inverters making up a three-phase system are better. Let's assume for a minute that I have like a three-phase system with single-phase inverters connected Y, like they're connected phase to ground. In that case, what's going to happen when I have my phase C fault? The phase C inverters are going to see an undervoltage and drop out. Phase A and B inverters are going to keep chugging merrily along. Now, that can be an issue because there's a big negative sequence current component there. I've got a two-phase source. Upstream transformers may have some issues with that. But in terms of overvoltages and things, no problem, right? No power rejection of the unfaulted phases, no ground fault overvoltage. It works just fine. But part of the thing that we can run into, and we've actually seen a few cases of this recently, is if I have three single-phase inverters, I form the island, whether it's faulted or not, those single-phase inverters, generally speaking, are not talking to each other in terms of maintaining 120-degree separation between the phases. So they may collapse. They may do something like this. If they do that, now I can get negative and zero sequence currents. I've actually got a negative and zero sequence source on the PV side. So depending on what my negative and zero sequence circuit impedances are, we can get voltages from there. So the jury's still, the jury's still out just a little bit on how to deal with three-phase systems made up of single-phase inverters. There are some advantages to the single-phase inverters, and we want to try to take advantage of those, and that's what we're working toward. I wanted to show you this case, too, that I mentioned before. If your DG is on the grounded Y side of a transformer and there's a delta on the other side, then you can have a ground fault over voltage on the delta side. And where we used to see this all the time was with existing facility transformers. You'd put a PV plant on the target store. The target store's facility transformer was delta on the high side to isolate its fault current concerns from the utility's fault current concerns. Then what happens in a case like the one that I've shown on the screen here is this is a substation, obviously MATLAB Simulink model for those of you who suffered through MATLAB Simulink before. But you will notice that there is a substation transformer there, this delta on the high side, grounded Y on the low side. It's impedance grounded. This is part of the beauty of MATLAB, by the way. There's so much flexibility here. We're going to get into that in a minute. But we've got this transformer set up with the substation ground grid. Right now we've got 150 milliohms of impedance to remote earth in the ground grid. But the point of all of this, you notice there's that three-phase breaker over there. That's my feeder breaker. If that's the one that isolates, then I'm worrying about the circuit downstream. But what happens if I have a single-phase to ground fault between the two orange blocks up there? The top orange block is the utility source. So we're going to pop a breaker that's upstream there. Now I've got a single-phase to ground fault on the delta side of the substation transformer. If the DER was big enough that it's back feeding up through the substation transformer, now I can have a ground fault over voltage up there on my sub-transmission or whatever that is upstream of the substation transformer. So we can end up with issues where there's ground fault over voltage up there. The main mitigation strategy for this right now is 3V0 relaying. You usually don't apply a grounding transformer here, and I'll show you the reason why. It has to do with the overcurrent protection of the grounding transformer. What we would like to be able to do for the future is we think there are some ways to deal with this at the DG site using symmetrical components. And it would be negative sequence relaying is what we're going to be looking at. So that's where this is headed, we think. Here is a case of a single phase to ground fault. The generation to load ratio is set to 1:1 in the island. And this is an inverter source, ungrounded inverter source, with a grounded Y to grounded Y GSU transformer. So this is the case in which we said we shouldn't get a ground fault over voltage. And it turns out we don't. You'll notice there is a small over voltage. We get about a 17%, 1.17 per unit over voltage on this. But you'll notice what's happening here is that phase C voltage drops really, really low, and that power then gets rejected to phases A and B, which causes their voltages to rise just a little bit. So that's what's happening here. Notice that they're all still pretty well centered around zero, right? So this isn't that neutral shift issue we were talking about. We just don't see it. Notice the red text again across the bottom of the screen. Once again, all the voltage and frequency relaying is turned off. This inverter actually would have tripped immediately after the utility breaker opened on either under frequency, in this case, over frequency or under voltage, because you see what the phase C voltage is. So again, this is a little bit misleading for how long it lasts, but this is to enable you to see the full transient. Here are the sequence voltages during that exact same event. And what you can see is that there is some zero sequence in there, but the negative sequence is much, much more prevalent in this case. And that is the problem that we run into. This is a positive, negative, and zero sequence phenomenon. And the reason why that's important is you can't mitigate the other components of this with a grounding transformer. So the mitigation strategy has to change a little bit to make sure that this is going to work. I threw this plot in here to show you the average per phase power during this event that we were just looking at. And the reason is so that you can actually see the power rejection to the unfaulted phases. You notice that phase C's power drops to 0. Phases A and B go up. That the inverter is trying to figure out how to get that power out. So it raises those phase powers up to try to do that. How do we mitigate a ground fault overvoltage? Well, we've seen already that with a synchronous generator, if you are ungrounded, ground fault overvoltage is real. That is going to be a problem. How do you fix it? Well, use effective grounding. You put in a grounding transformer. IEEE 142 is a standard that tells you how to do this. It's a well-known, it's the green book. It's a well-known problem that has a known solution. So that is a simple one to take care of. Just ground the thing. If the generator is internally grounded and like has a grounding transformer built into it, you might need some kind of a grounding reactor to moderate the fault currents, but you wouldn't need a separate grounding transformer in that case because it's already in there. Now, how about inverters? Well, why not just apply that same philosophy? Just say, hey, throw a grounding transformer out there. Well, there's actually 4 reasons, and unfortunately, as I'm looking at this slide, the most important reason isn't on this slide. The biggest reason is that with inverters, it's not strictly a zero-sequence derived neutral shift phenomenon. So a grounding transformer actually won't fully mitigate it. It's not an effective way to do this. One of the big things from the CUSP perspective, or from protection's perspective, is that, as you know, every grounding transformer that we put on the distribution circuit will make a contribution to the fault current for any asymmetrical fault. So envision a situation where you've got 4 or 5 photovoltaic plants on a feeder, put a grounding transformer on every single one of them. It's going to completely mess up our protection coordination. So that's not desirable either. What we want is a grounding transformer design procedure that offsets that problem by trying to take only the part of the fault current that is attributable to that PV plant. And I'll show you a procedure that does that in just a minute here. Adding grounding transformers does add to the cost of projects. So obviously that's a reason we don't want to do it. It just increases cost. And like we said, we're trying to do minimum cost here. Last but not least, there is some evidence that if you hard ground the neutral point on an inverter, that actually causes some increase in the output distortion. And the reason appears to be because if you don't ground the neutral wiggles around a little bit as each of the 3 phase legs it's doing its switching thing. If you fix that point, now those wiggles are going to be reflected out to the phases. So there is some degradation in inverter performance that could be expected if you hard ground that neutral point. So the question that, of course, we are all asking is, okay, do I need a grounding transformer or not? Yes or no? And, of course, the answer is yes and no. I'll give you the good engineering answer. It depends. Of course it depends. Well, if you have a GSU transformer on your PV plant that's YG, grounded Y on both sides, then the answer is no, you don't. The grounding transformer would be mitigating a problem that doesn't exist. So you really don't need it if that's the way your GSU is set up. If you have a GSU transformer that does not have zero sequence continuity, then you got to take a look at it. So the answer may be yes in that case. So it does depend. My recommendation is if you can set up the PV plant with a YG GSU transformer, that's really what you want to do because that solves a lot of problems. There's an issue, we were just talking about this a minute ago as well during the break, that some photovoltaic inverters today don't want to face a grounded Y winding on a transformer. And it has to do with the way they detect arc faults on the DC, or ground faults on the DC side. If we have 2 grounds, an AC ground and a DC ground, their ground fault protection is going to be tripping off all the time. So they want an ungrounded AC connection. And really, that's where a lot of the problem comes from. So time to start working on figuring out how to solve that problem. Here is the set of sequence networks with a grounding transformer present. The change here, of course, is I've got that Z0 G that provides my zero sequence path, my zero sequence continuity. But you'll notice, even if you do require the grounding transformer, I still need to include the loads in the sequence networks. Why? Well, because the grounding transformer is still open in the negative sequence. So I still won't have the negative sequence modeled right if I don't put the loads in there. We're just kind of stuck with that. So let's assume for a minute, I've been harping on, hey, you don't need a grounding transformer. What you want is a YG-YG GSU transformer. Well, unfortunately, sometimes I can't use a YG-YG GSU transformer because of the issue we just talked about. Some inverter manufacturers don't allow that connection. So if I'm forced to use a GSU transformer that breaks the zero sequence continuity, I do need to make sure the feeder remains effectively grounded. How do I do that? Well, I'm going to put a grounding transformer out there that is going to maintain that zero sequence path. Now, there are a couple different ways you can do this. You can make the GSU transformer grounded Y on the feeder side, delta on the inverter side. That is a grounding transformer as seen from the circuit side. So that's one way to do it. The other way is just drop a zigzag or a typical grounding bank onto the MV side of your GSU transformer, the medium voltage, high voltage side of your GSU transformer. What I'm going to show you now is a process by which you can size that thing so that, in theory, it should minimally impact your protection coordination. This is a procedure that we developed. It was published at the Western Protective Relay Conference, Schweitzer's conference out in Spokane. The background math is all in that paper. I'm not going to get into it today because of time, but if anybody wants to see that, my email address is on the last page of the slides. Just drop me a line. I'd be more than happy to share that paper with you. And incidentally, we welcome your comments on it as well. This is a process that is still being vetted to a certain extent. So for a grounding transformer, there are 6 electrical parameters that I need to specify. I need to know the terminal voltage, which is just the voltage where I'm going to be hooking it up. So generally, we do know that. I need to know the zero sequence fault current. In other words, during the asymmetrical fault, the grounding transformer is going to be taking the zero sequence current. How much current is that? So the transformer's got to be rated for that current. What is the duration of that zero sequence fault current? Usually, in the past anyway, we have been taking 2 seconds. And where that came from is the IEEE 1547 recommended maximum run-on time for an island is 2 seconds. And obviously this phenomenon only happens after we've opened the substation breaker. So we should be offline within 2 seconds anyway because of anti-islanding. That's where that came from. Now I will tell you, we've actually been using a longer time for this. About 10 seconds is our recommendation right now. I'll show you the reason why in just a minute. It has to do with coordinating the overcurrent protection of the GSU, of the grounding transformer. Okay, so I need that duration, and this is something that we just choose. I need the continuous circulating current, the zero sequence circulating current. In a distribution feeder, there's always going to be some level of voltage imbalance at the point where I'm going to put this grounding transformer. That imbalance is probably going to have some zero sequence voltage component, and that zero sequence voltage will drive a circulating current in the grounding bank. So I need to know what that is, and the grounding transformer has to be rated to handle that continuously. And then last but not least, I need the zero sequence resistance and reactance. I need the impedance of the grounding transformer to make sure that the coefficient of grounding remains where it needs to be. For those of you who are counting, I said there are 6 parameters, but there's only 5 bullets. You notice the last bullet actually has 2 parameters in it. So I can count. You'll notice one parameter that isn't on here, and that's the KVA rating. And this is another one of those sort of esoteric things that any time we talk about a transformer sizing, first thing that comes up is what's the KVA rating? Yep, that's logical. That's what we all do. But the thing is, that's a load-serving transformer, and the KVA rating is how much load throughput does it have. What we're talking about here is handling circulating currents, and there's no load. It's not a load-serving transformer. So you can get a KVA rating, but in general, the manufacturers don't specify them that way because it doesn't really mean that much. So lots of times on a grounding transformer, there is no KVA rating specified, and most of the manufacturers won't ask for it. So how do I get these? Now, I mentioned before, obviously I'm glossing over a lot of background math here. Anybody who's interested in it, don't hesitate to contact me. I'd be more than happy to talk to you about it. First thing we need to do is find the resistance or reactance of the grounding transformer. And what we recommend at this point is using a recommendation that comes from IEEE 1547.8. What we do is you find the base impedance of the PV plant, and you do this in the usual way. You take the interconnection voltage squared divided by the apparent power rating of the PV plant. And because we're talking current here, you want S, not P. if the inverter is operating at non-unity power factor. Then, in order to maintain the correct coefficient of grounding, but while trying to make sure that the PV plant only accepts its part of the fault current and doesn't mess up the protection coordination, we recommend using a reactance for the grounding bank that is 60% of the PV plant base impedance. That's where this 0.6 times Z base PV comes in. Again, bunch of background math behind that. But that recommendation is straight out of IEEE 1547.8. Then, again, to maintain proper coefficient of grounding conditions, we're going to require that the ratio of the reactance to the resistance is greater than or equal to 4. So limit the resistive part of the impedance is what that's all about. So now I've got my two impedances. Of those 6 parameters that I said we had to have, I've got 4 of them. I have the duration, I've got the terminal voltage, and now I've got the RG and XG. So I still have to find those two currents. I need the fault current and the circulating current. How do we do that? And finding these is what most of that WPRC paper was all about. To find the circulating current, what we did is we said, okay, we know that there's going to be a certain fraction of imbalance in the voltage at that point in the feeder. That percentage imbalance is expressed as a variable P, and that's the P that you see in the equation here. I apologize for using P. It looks like power to me. I should have used something else, but we'll change that for the future. In any case, so that P there is the percentage imbalance that I expect. Once I know what that is, what is the zero sequence voltage associated with that percent imbalance? That zero sequence voltage then is applied to the grounding transformer impedance, and that's where I'm going to get my continuous circulating current. So that's what we've got here, and you'll see that when you run the math, what you're going to get is it's P times VA1 divided by 2 times the square root of 3 times the grounding transformer impedance. And you notice the 2 is gone. What happened? Well, as you might imagine, there are a couple of assumptions that are baked into this analysis. One of them is that we maintain 120-degree phase angle separation. One of them is that the imbalance is roughly symmetrical. In other words, if phase B is in the middle, phase A is 5% up, phase C is 5% down. Neither one of those is strictly true in the field. So we ran a big parametric set of simulations to figure out how much difference does that make. Because obviously we want to keep the relationship really simple. And what we found is that if we simply doubled it, in other words, drop the 2, you get a result that is conservative. So that's what happened here. We took the exact result, then to mitigate the impacts of the assumptions, just doubled that. And that's the recommendation that's made here. And again, that doubling, that's not a guess, right? We ran lots and lots of simulations to figure out what is the actual impact, what's the sensitivity of changing the phase-to-phase angle separation, what is the sensitivity of moving that imbalance point so that it's not symmetrical. And this was the result that we came up with. And it still results in a really nice, simple, easy-to-use expression. It gives us a conservative estimate. Last but not least, I need that 2-second fault current rating. And what we do there is we say, okay, we went back to that symmetrical component diagram, coupled together at the fault. What is the worst voltage that can show up on that grounding bank zero sequence impedance? The absolute maximum voltage we could get would be basically if all the other impedances in the system were 0. So I've got VA1 directly applied to the grounding transformer. And you notice that's exactly what this equation is. That's it. We just applied the positive sequence utility voltage straight across the grounding transformer. That's assuming all the other sequence impedances are 0. Obviously they won't be. So again, in theory, this should be a conservative estimate. It should be a high side, which is what we want because obviously we don't want these grounding transformers turning into glowing puddles on the ground. So it's important to try to get these things right. Grounding transformers should be protected, and this is where some of the earlier discussion is going to come back. You got to have overcurrent protection. It's really nice if you also have thermal overload protection. Most people don't do both. We just do overcurrent. So as I mentioned here, there's a case where the grounding transformer should be acceptably sized from the procedure you just saw to handle normal circulating current and fault current. But you notice there's the second sub-bullet here says there can be an abnormal imbalance. Remember we talked about temporary versus transient overvoltage. Well, I can have a temporary voltage imbalance. For example, I get a large single-phase lateral that trips. So that all of a sudden, I was expecting, typically 5% overvoltage. Well, for a while, I'm going to have like a 10%. I'm sorry, I said 5% overvoltage, a 5% imbalance. So for a while there, I'm going to get like a 10% imbalance until a line crew can get out there and fix the fuse, probably a fuse on a single-phase lateral. So for quite a long period of time, I might actually have an overcurrent condition where the grounding transformer is just not sized for that. So you have to protect the grounding transformer against that. And what you do for that is just standard time inverse current, overcurrent protection. The thing that makes this a little more complicated is that if I trip the grounding transformer, I also have to trip the PV plant. And the reason, of course, is the whole reason the grounding transformer is there is because I have this ungrounded source. If I take away the grounding transformer, I've got to take away the ungrounded source. If the PV plant and the grounding transformer are right next to each other, that's not that hard to do. It can be a little challenging just because of logistics. Sometimes it's hard to find devices that do this at minimum cost. But the case that we were talking about a minute ago is, let's assume that my delta winding that I'm trying to protect is that substation transformer. So that may be 5, 10, 15 miles away from the PV plant. Well, if I was going to put a grounding transformer up there, which I could do, right, that would solve the problem. But I got to run a cob link from there all the way back to the PV plant to basically do a shunt trip. Well, if you're going to do that, just do direct transfer trip, right? There's no reason for the grounding transformer. So, well, I guess you'd have to transfer trip from the transmission breaker, so there may still be a reason to do it. But this is, what I said before, is normally we do 3V0, because then you can do it all locally. And what we are working on now is being able to do it actually at the PV site. And so far, luck has been pretty good with that, but it's not ready for prime time yet, which is why it's not in here. But I think there is a solution to that can be handled locally at the PV. And I mentioned before, we've been recommending you might want to set the fault current rating for higher than 2 seconds. You might want to go for like 10 seconds. Or you might want to go for a higher percentage imbalance. Don't use 5, which is our standard. If you can afford it, if it doesn't jack the cost of the grounding transformer up too far, you might want to go with something more like 10. And the reason is because you're trying to come up with a compromise between the cost and sizing of the grounding transformer and the problem of tripping the PV plant offline all the time every time there's an overload that causes the grounding transformer to trip. So that's the reason why we're saying you might want to up those recommendations just a little bit, because it would give you a more favorable trade-off between trips and protection. But the key is you still got to be adequately protected. The grounding transformer sizing procedure that we gave here should enable you to do that without messing up your existing protection coordination. That's the point. Okay, so all of that was on ground fault overvoltage. We're going to talk a little bit about load rejection overvoltage now. So we're going to switch overvoltage mechanisms. Before we do that, does anybody have a question on ground fault overvoltage? Sort of the bottom line of the whole thing is that if you've got inverter sources and YG transformers, ground fault overvoltage doesn't appear to be a problem, which is great news. Unfortunately, you don't always have that case, so got to pay attention. Now let's talk about load rejection overvoltage. What is this? Basically, the very short version is load rejection overvoltage can happen if I form an island with a generation to load ratio much higher than 1. So in other words, I've got a section of the system that was exporting to the rest of the system. I pop a switch so that now that power that was being exported has nowhere to go except into the local loads. The generators don't respond instantly, so the power will moderate, but it doesn't happen right away. And during that brief period of time, I'm forcing all that power into those local loads, and Ohm's law says voltage goes up. The isolated section, you can see that load rejection overvoltage is very different from ground fault overvoltage, because with ground fault overvoltage, that's a 3-phase phenomenon with a 4-wire circuit and an ungrounded source, blah, 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 right? Load rejection overvoltage can happen anywhere. It can be on a single-phase lateral. It can happen for any combination of phases. It can happen for segments of circuits. No matter how your circuit is configured, if the generation to load ratio is higher than 1, you can get an LROV. In theory, you can get LROVs that are well in excess of 2 per unit. I mentioned 2.25 here, and I had the 2.5 on the previous slide. That was just sort of a conservative version of this 2.25. Where the 2.25 comes from is there was some really good lab testing done not long ago by Southern California Edison. I think that those tests are now about 5 years old. But they looked at a bunch of single-phase inverters, and then they would put them in a system, they'd get them up to full power, and then they would open circuit the terminals of the inverter, no load. For some of those, they saw voltages pop up as high as 2.25 per unit. So obviously that's a concern. Now, some of these test results should be taken with a little bit of a grain of salt because they're older inverters, they're single-phase inverters, and also it's an absolute, it's 100% load rejection. For us, we don't care so much about that case because if you are a distribution engineer, you don't necessarily care if the inverter damages itself. Right? For me, I care about that a lot because I don't want the inverter to blow up. But if it does that to itself, that's not the utility's concern. The utility concern is what happens to loads. So the 100% load rejection case isn't really the worry. I should be a little cautious about that because you can form islands in which the only load on the inverter is arresters, and the utility does care about that. So there's some things that you have to pay attention to. So here's our distribution circuit again. You'll notice I've added this big blue arrow showing the power flowing out of that section of the system. It's flowing through that line recloser LR2 there. So what I'm going to do now is turn LR2 green. We're going to pop that breaker open. This is the case where a load rejection overvoltage becomes a concern. That excess power that was going through LR2 now has to go into all those loads inside the island. And like we said before, if you think about it from an impedance load perspective, Ohm's law says, hey, power went up, the voltage is related to the power by V squared over R is equal to P. So R didn't change, P went up, V's got to go up. Part of the reason why we take such pains to differentiate LROV and GFOV is that, as I mentioned before, strict classical GFOV is a strict classical GFOV is a zero sequence phenomenon. Be careful to get these right. LROV can be positive, negative, or zero sequence, any combination of the three. For example, what if I have a balanced three-phase source feeding an island with a balanced three-phase load? It's just that the load per phase happens to be less than the source per phase. I could get a balanced three-phase LROV in that case, all positive sequence. So there's not necessarily anything in any of the other sequence components, depending on how the system is set up. I mentioned before that if we have a single or two-phase interruption, like a single-phase open, you can get an LROV just on the single-phase open. If you have unbalanced loads, you can get some really odd things happening. For example, if I have a balanced I have a balanced source, but I have a load with a different power factor on each phase, which typically is the way it is, right? They're not all equal. Then what happens is when I look at the voltages, not only do the magnitudes change, but the phase angles all change. And you get really odd-looking voltage vectors in the island. So, and I mentioned this before, that both LROV and GFOV can include zero sequence voltage, but they're completely separate physical mechanisms because notice you can have an LROV without a fault. GFOV assumes a ground fault. The GF is ground fault. So an LROV just means I have to open the switch. This could be a sectionalizing operation, a manual source transfer, anything like that. Here's that LROV during an islanded case where the load was significantly unbalanced. You'll notice that this is a resistive load on all three phases. So I've got balanced currents going in, but I'm going to get very unbalanced voltages coming out. If I have impedance loads, in other words, LR loads or LRC, then I can actually get the phase angles changing between the voltage vectors as well. So you can get some kind of strange looking things coming out of this case. How big does LROV get? Now I mentioned before in this case where we had 100% load rejection, so you basically be like an infinite generation to load ratio. They saw about 2.25 in the lab as the worst case. And I should point out, by the way, 2.25 was the worst. Many of all the inverters were less than that, other than that one. So you have to take that with a little bit of a grain of salt too. But for us, for our case from the circuit perspective, generally it's the worst case that we're interested in. Well, I mentioned before, if you look at the relationship between voltage, power, and impedance, assuming a constant impedance, constant resistance load, let's start with a simple one. then V squared over R equals P, right? That's the power relationship. So if I've got a constant power source, which is what the PV is trying to do, and I isolate it with a resistive load, I would expect the level of overvoltage to be equal to the square root of the generation to load ratio. So in other words, if I have a 2-to-1 generation to load ratio, purely resistive load and a purely constant power source, I should get a 1.41 per unit overvoltage. And you see the curve that's plotted here is just that relationship. Theoretically, that's what we would expect. Now, as I've said before, all of these theoretical values tend to be a little bit on the high side. What do we actually get? I have been a part of a team that's been working with the National Renewable Energy Lab, also with Solar City, the system developer, to look at load rejection overvoltage and ground fault overvoltage in a lot of detail. What you see on the screen in front of you are some load rejection overvoltage numbers measured by the National Renewable Energy Laboratory. And I will point out that these results are a part of a publicly available report. If you type load rejection overvoltage into NREL's search engine, it'll pull it right up. If you would like to see it and have any trouble finding it, contact me and I'll get it for you. But NREL produced a really slick report on this and detailed these results. And what we see is something that looks like this. This is the average load rejection overvoltage. It's not the worst case. But what you can see is that we do get that it kind of asymptotes out, kind of the way we expected it to. But it's at a much, much lower value, and it's flattening more than we thought. You know, the square root curve that we saw would never totally flatten out. This one kind of sort of does. And we start looking at this, notice that you get up to a 10-to-1 generation load ratio, and you've only got a 1.6 per unit overvoltage. Now, of course, that's high. I don't want to trivialize a 1.6 per unit overvoltage. But it's not nearly as high as you might have expected from the theoretical consideration, which would have predicted well over 3, right? Square root of 10. The real surprise was when you dig into the NREL results in that report, there wasn't a single case that violated the CBEMA curve. And to be honest, that surprised me. I figured we'd see at least some that did. They didn't. Inverters were, they got off pretty quickly and they just did not drive the voltage that high. What's going on here? Why did that work that way? Here's a simulated result. This is for a 5-to-1 generation load ratio with a purely LRC load. You'll notice that, again, we pop up to just shy of 2 per unit, but that's still well below the theoretical maximum consideration, which would have been square root of 5, right, which is over 2. So, and again, I keep pointing to this red text at the bottom of the slides. Once again, the voltage and frequency relays are turned off. For an overvoltage this high, that 1.2 per unit IEEE 1547 overvoltage trip would have caught this trip a long time ago. So again, take that with the appropriate grain of salt. But the point that I wanted to make here is that you notice this simulation produced quite a bit higher voltage than the lab results did. Why? What's the difference? Well, let me show you some of the mechanisms that are limiting the overvoltage. I mentioned one of them to you before, and that is that with an RLC load like this, a purely impedance load, in order to drive the voltage up, I've got to source the power, right? I got to have enough energy to hold that voltage up there. Well, the PV is energy limited. There's only so much behind the inverter. It can't do more than that. In this simulation, that is the main thing that happened. It got up as high as it could, and then there's just no more power, right? So it can't drive it all the way up to the square root of 5. But you notice it was higher than was seen in the experiments. We're going to come to this in just a minute. Why did that happen? I'll show you why that is. There's a specific mechanism. And I should, okay, well, sorry, I'm getting ahead of myself. Let's stick with what's on the slide here. So let's go to the rotating machine case. What about LROV and rotating machines? Now you guys, you're getting sick and tired of hearing me say this. We model a rotating machine as a what? Voltage behind impedance, right? Well, if I truly do have a constant voltage behind an impedance, what LROV do I expect? Yeah, I see some heads shaking. None, right? It's a voltage source. It's not going to drive the voltage higher. So the reason the inverters do this is because they're current sources. They're pushing current into impedance. So a rotating machine operating in PQ command mode, feeding constant power, constant VARs into the grid, may give you a little bit of an LROV because it's going to take just a minute to regulate that power out. So when you first get the situation, it might momentarily source more power. And of course, the frequency will drop when it does that. But when that happens, then the level of LROV is going to be very limited, again, by the fact that the generator is acting as a voltage behind impedance. So here's a case where this really physics-dominated generator is actually a big advantage for us. LROV should not be a significant issue. And I mentioned this before, that there's a lot of standard relaying that should be able to catch this. Frequency relaying, negative sequence relaying, standard overvoltage relaying, any of those should catch this and pop it off. Now, how about the inverters? We were talking about this before. We've seen what at first looked like some somewhat contradictory results. Why? This is a single-phase inverter bridge. I showed you a three-phase bridge before, and I've got a European example in here again. You see that the DC link voltage is labeled U. So apparently this is a German picture. But you'll notice that within the inverter topology, and I mentioned this back when I showed you the three-phase one as well, this one shows MOSFETs. But on each one of the semiconductor switches, there's a diode pointing the other way. There's an anti-parallel diode in there. Now, if you think about that for a minute, if I'm moving power from the DC side to the AC side, remember I said before, I got to have the DC voltage higher than the peak of the AC. So if I do that, then power moves DC to AC and everybody's fine. But what happens if I start getting an overvoltage and the AC voltage rises above the peak of the DC? The peak of the DC? The peak of the AC rises above the DC. What happens then? Well, look at this circuit. There's a rectifier in there, right? There's an anti-parallel backwards rectifier. There's a DC voltage over here, and what's going to happen is I'm going to clamp the AC voltage to the DC voltage. Remembering now that this is a current source, there's no actual supply or anything behind the DC voltage. Well, I guess I should be careful saying that because the PV arrays out there, that voltage is real. But the point that I'm trying to make is that if you look at what happens in some of these overvoltage cases, and this shows up a lot in some of the NREL waveforms, you'll see that the voltage starts to rise up and then it just squares off, just clamps it off. What's clamping it? Well, it's this anti-parallel rectifier, and that's why you see that asymptoting of the voltage. Whatever your DC voltage is, it's not going to go above that. Well, then why were the results different between the simulations and the experiments? Well, the reason is because most of the experiments were using 600-volt class DC inverters. That simulation I showed you was a 1,000-volt DC inverter. So again, now the clamping mechanism didn't kick in. What did kick in? Well, it's the power limited mechanism. I still don't get all the way up to that theoretical voltage. So it's really depending on specific inverters and what's going on. Now, I mentioned before, one other thing I should throw in here, that the semiconductor switches and inverters are heavily protected against overcurrent. There's a lot of protection here against overvoltage too. So the inverter will self-protect in ways that tend to limit the LROV. So mitigation. What do we do about this? The first bullet that we got up here, the picture's not completely clear. It's beginning to look like LROV may not be such a significant issue. It may not be something we have to worry about too much. Because again, we've got these clamping and self-protection mechanisms. We've got this power-limited mechanism. And as I said before, so far within the experimental results that we have from NREL, there were no violations of CBEMA. So it's kind of looking like, hey, maybe this is going to be okay. There is further testing and modeling going on because we still have to look at these higher DC voltages. There's some things that have to be examined. But the good news is the inverter looks like it is able to handle this problem itself, either by very fast action or by this clamping that we've been talking about. Now, the thing is, that is actually a really, really nice thing. Why? Well, because if it didn't do that, really our only mitigation strategy is to limit the amount of distributed generation you can put on the feeder. There's nothing else you can do. Why do I say that? Well, because a lot of people say, hey, just use DTT, right? Well, unfortunately, the load rejection overvoltage can jump up to its maximum value in the first cycle after the switch is opened. Generally speaking, DTT is not that fast. It's going to take you 4, 5, 6 cycles maybe to get the generation off. If you did have an overvoltage that would result in a problem, DTT is generally going to be too slow. So that's not going to be our answer. So the real key is this needs to happen within the inverters, and it looks like the good news is it actually does. So stay tuned, but I think LROV is looking like it's not going to be the concern that we had once thought that it might be. Okay, I'll talk just a little bit about protection coordination.
That's about 12:15, just to let you know.
Got it. And were we going to go 12:30 or did you want to?
It's up to you.
Okay. This section's pretty short, so maybe we'll just go through this one and then we'll break for lunch. Okay, I'm getting hungry too. So next section, I just wanted to talk very briefly about protection, coordination impacts. But the good news is we've already pretty much talked about all of this, right? That of course, with protection, the first thing you have to talk about is protection of what? What we are talking about here is protection of the phase conductors from overcurrent. So transformer protection, inverter protection, all that's separate and will be dealt with elsewhere. But what we want to make sure of is that we don't mess up our ability to protect the phase conductors against overcurrent, and that's all about fault current contribution. How much fault current are we getting? As we have said before, the inverters themselves contribute very, very little to fault current. About 1.2 per unit is our typical assumption. We find most inverters are actually lower than that. I mentioned before that the recommendation in IEEE 1547.8 is based on a 1.6 per unit fault current contribution. At least I think I mentioned that. If I didn't, I intended to. But that's a part of where that comes from. So it's very conservative. But we've said this before, that if you've got an inverter source that is connected to your feeder through a YGYG GSU transformer, there really should be no impact on protection. You really shouldn't have to do anything. So that's the good news. Now, of course, if we've said this before, if you can't use a YGYG generator step-up transformer, there can be a fault current contribution from my grounding transformer, or from whatever it is that's mitigating my grounding. So mitigating my ground fault overvoltage. So you have to watch out for ground fault impacts, ground fault current impacts from those. If you follow the procedure that was outlined here just a little bit ago, again, in theory, that should not be an issue. So again, the reason why that grounding transformer sizing procedure is the way it is to prevent impacts on protection. So hopefully we're going to be okay. We're going to be okay with this. I mentioned before that we got this 1.2 roughly per unit contribution to fault current from inverters. If you have a lot of inverters, well, it could add up to a lot of 1.2 per unit fault currents. So if you've got a dozen PV plants on feeder, well, then you may want to start taking a look at how much fault current is being contributed. So that's one thing. If you do have an issue like that, generally speaking, things start to get really interesting because we've got these current limited sources that are now starting to dominate the protection situation on the feeder. The first thing, you can try to adjust the time current curves, but that's not always a feasible solution because, again, what's happening is that the PV is offsetting part of that from the other end of the feeder. So sometimes you can't just fix the problem by changing the time current curves. If you have a situation where your fault current is being dominated by inverters, usually I can't use fuses. And the reason is because the maximum fault current from the inverters and the minimum current from the loads are too close together. I can't coordinate in between there, and the load may blow the fuse or the inverter may not blow the fuse. So that kind of just standard overcurrent protection may not work in a case like this. If it doesn't, we have had really good success with negative sequence relaying. Impedance-based schemes can work, again, depending on the specifics of your circuit. We really love to use, there are several different variants of differential protection that we've used, especially in microgrids and low inertia systems that work really well. But, of course, they're costly because you've got to have the comm channels, the networking, and all that stuff. That costs a lot of money. So you usually don't use those unless you have to. Sometimes you do. If you're in a microgrid that's all inverter dominated, that may be your best bet. And there are some novel methods. We have developed some at our company. There are some others being developed by other workers. That there's some solutions being developed by this. Again, I'm not talking about them today because they're not really ready for prime time, but stay tuned to this because I think there's some solutions coming forward for this problem. That's the good news. If your DERs are rotating machines, well, you're sunk. That's going to impact your protection coordination, and you will have to set up the protection with the rotating machine in mind. There's a number of things that you can do. One thing that we have had some luck with is that now, one thing we've had some luck with is that we put in relays, and then the relays have a directional element. So you know which direction the fault current is coming from. You know what the fault current contribution is from the utility. You know what it is from the sync gen. So depending on the direction, just pick the right set of TCCs to isolate the fault. Now, of course, the problem with that is you have to do it with relays. You can't do it with fuses because fuses only have one setting. It doesn't matter which direction the current is going. There are some mitigation strategies I've listed here. And again, it's kind of the same thing we've talked about before. You can use some adaptive protection. If you do that, make sure that it's modeled, properly tested. Transient modeling, hardware-in-the-loop modeling are both good. You can limit the allowable DG rating again, too. That's another option that, as we said before, we try to avoid. I wanted to just mention a little bit Flizzer. I don't know how many of you have ever used the term Flizzer. I like to call it Flizzer because I like to say Flizzer. But Flizzer stands for Fault Location, Isolation, and Service Restoration. Other names for it are automatic circuit reconfiguration, automatic system reconfiguration. But those acronyms aren't as fun to say as Flizzer. It's, what the situation is here is it's one of those cases where I've got a normally open tie to a second source. And of course, we do this all the time in distribution, right? I'll take a part of a circuit and switch it over to another source. All Flizzer is doing is automating that process. I'll have a set of relays that are talking to each other on the feeder. Then if a fault occurs, then the relay that is upstream but closest to the fault should be the one that opens because I've got them coordinated. Then they talk to each other on the communications network. They say, okay, who was the last one to see the fault current? And one of the relays says, hey, that was me. Then they say, okay, who was the first one who didn't see the fault current? And the next relay says, hey, that was me. So the fault is between them then. And you can open these, then you can reclose on this end to pick up the head end of the feeder and close into your secondary source to pick up the tail end of the feeder. And the idea then is that you may have a situation where, previously, a truck runs into a pole and knocks it down. You might have had 100 customers out for 8 hours while you're putting the wires back up. Now you're going to have 20 customers out for 8 hours and 80 customers out for 40 seconds while the circuit reconfigures itself. And the system reliability indices are greatly enhanced by that. Well, you can see right away that could be a challenge, right? Because this breaker is saying, who was the last one to see the fault current? And this guy says, yeah, I saw it. But now I got a DG over here and say, okay, who was the first one who didn't see it? Well, we all saw it. What are you talking about? Everybody on the feeder saw it. So you can still pick up the head end, right? Because you can open this one and all that kind of stuff. But I guess we already have picked up the head end because it never isolated. But the bottom line is that DG can mess up Flizzer schemes. What we've seen is that, again, with inverters, usually you can kind of retune the Flizzer scheme a little bit to handle that. If there's a rotating machine in there, you have to use some form of adaptive protection, like what I was talking about, where the direction of the fault current is monitored. And for Flizzer, that's great, right? Because I've got all this fault current coming from the utility this way, but now I'm sourcing a bunch of fault current from the sync gen, and we just say, hey, I saw it, but I saw it this way. Hey, I saw it, but I saw it this way. The fault's between them. So I can still find it and isolate. What we have found with inverters is that Flizzer still works mostly. About 80-85% of the time, it still will work because the fault current contribution from the inverters is so limited. In those cases where it doesn't work, what happens is it misidentifies the zone. So you may actually have 2 zones that get isolated instead of just the one. You'll have a few more customers out than you might have ordinarily had. We've seen a very, very limited number of cases where it actually misidentifies the section. So that it says, hey, I didn't see it, I did see it. It closes in, but the fault is still in there. And it's, whoops, then you just end up doing it again. So obviously you want to avoid that because you don't want to be slamming breakers back and forth or re-energizing the fault. But usually it is possible to re-coordinate things so that Flizzer can still work. Again, modeling is very, very helpful.